Why doesn't our periodic table go on forever? Why don't we have, for example, elements with 300 protons or say 1,000 protons? Well, the short answer is because heavier the elements, the more unstable they become. For example, elements above atomic number 83, they don't even have a stable isotope. All their isotopes are radioisotopes, which means sooner or later, these will decay. And if you consider even heavier elements, well, they will decay almost instantly and there's no chance that they exist in nature. But why are they unstable in the first place? And how do they undergo decay? And how do we use this to create smoke detectors? Let's find out. So let's start by asking ourselves, why do heavy nuclei become unstable in the first place? Well, the answer is because there are two forces of nature at play over here which are acting against each other. The first one is the good old Coulomb's repulsion, the electric force. All the positive protons are repelling against each other. This is what tries to blow the nucleus apart. But then what keeps the nucleus together in the first place? Well, turns out there is a force even stronger than that, the strong nuclear force. And this force is an attractive force, and that's what keeps the nucleus together. And it does so because strong nuclear force has two advantages over the electric force. The first one is it is the strongest force of nature, so that's amazing. But there's another one. You see, the Coulomb's repulsion, the electric repulsion, is only between the protons because it's only between charged particles. Neutrons do not participate, right? However, when it comes to strong nuclear force, both protons and neutrons participate. So they're all involved in the strong nuclear attraction. This is why a lot of stable nuclei exist in our nature, because the strong nuclear attraction just overpowers the electric repulsion or the Coulomb's repulsion. But compared to the electric force, the strong nuclear attraction has one disadvantage. That is, it is a short-ranged force. What does that mean? Well, if you concentrate on just say one proton, then it is being repelled by all the other protons in this nucleus, regardless of how far the other protons are. Because electric forces are long-ranged. It doesn't matter how far they are, the electric force works. And so it's being repelled by all the other protons. But the nuclear force is short-ranged. This means even though it is super strong and everything, only the few protons and neutrons in its vicinity, they are the ones in its neighborhood, they're the only ones that can attract it. The ones that are far away, well, they can't reach it. Their nuclear forces are short-ranged. Now, for lighter nuclei, this is not a problem because it is very small. So most of the protons and neutrons are within the nuclear range. But what happens as the nucleus gets heavier? Well, just imagine an extreme case. If there were lots and lots of protons and neutrons, all the protons will repel it. So the electric force becomes incredibly large on this proton. But not all the particles are going to attract it. Only the ones in the neighborhood are going to attract it. Which means if you have too many particles and the nucleus is too big, eventually electric force will overpower our strong nuclear force, and that's what will make it unstable. And so now hopefully you can see how or why, as the nucleus becomes more and more heavier, it becomes bigger and bigger, and because of the short-range nature of the nuclear force, eventually electric force can win out. That's what makes these things unstable. So if you now imagine elements with thousands of protons, there's no chance that they will stay put. The electric force will just blow it apart, it'll just break instantly. But what about the heavy elements that we do have in the periodic table? Well, over here, the strong nuclear force can kind of hold on to them, but not forever. They have found a way to become more stable. How? Well, they just spit out a helium nucleus. And we call this the alpha decay. We call it the alpha decay because when we first discovered it, we didn't know which this particle was, what particle this was, and we just called it the alpha particle. But later on, we realized that it's just a helium nucleus with 2 protons and 2 neutrons. Okay, this might raise a lot of questions now. The first question could be, how does this make things stable? Well, you can see the daughter nucleus now has less particles in it, so it's slightly smaller than the parent nucleus. If it's smaller, it's that much easier for the strong nuclear force to hold on to it, and therefore it becomes more stable than the parent nucleus. Now, that doesn't mean that this is completely stable. This might still be a radioisotope, and it might further undergo more alpha decays, which is totally possible. Okay, but then a follow-up question that comes to my mind is, why a helium nucleus? Why not anything else? Why does it spit out precisely this? Well, the short answer is because helium nucleus is incredibly stable. And so it's just more energetically favored, and therefore that's what happens. Okay, another question we could have is, when things become stable, the energy decreases, right? This should now have less energy compared to the parent nucleus. That's what it means to be stable. But if that's the case, where did the energy go? Well, that energy comes out as the kinetic energy of these particles. The alpha particle will take up most of the kinetic energy, but the daughter nucleus will also have some recoil as well. And now guess what? These alpha particles can go and hit other atoms, make them jiggle, causing heat. This is how radioactive heating works. And fun fact, folks, we believe this is majorly what keeps the Earth's core pretty hot. I mean, there are some other reasons, but we think this is the major one. And another fun fact, this is where most of the helium on our planet comes from the radioactive decay of elements found inside the Earth. Anyways, let's now familiarize ourselves with this and take a couple of examples. One example could be uranium-92. Turns out it will undergo an alpha decay. The question for us is, what happens after the alpha decay? Can we predict what the daughter isotope would look like? Well, let's see. Here's how I like to think about it. I know if it's an alpha decay, then a helium nucleus comes out. Therefore, my daughter nucleus must have 2 less protons in it. It started with 92 protons, 2 less protons, which means that daughter nucleus should have 90 protons in it. Similarly, my daughter nucleus will now have 4 particles less in total. It started with 238, now it has 4 particles less. That means it should now have 234 particles in it. That should be its new mass number. So my daughter nucleus should look like this. But what is it? I don't remember what is the element. It's not uranium anymore because it is 90, and I don't remember, and you don't have to remember. That's why we have the periodic table. If I just look at the periodic table, I see 90 to be over here. So this is thorium. Thorium. So look, we get a new element altogether. And if you look at the periodic table, you can see we've gone from uranium to thorium. So that means we hop 2 to the left in the periodic table. That kind of makes sense because you're losing 2 protons. So you hop 2 elements to the left. Okay, why don't you try one? In this example, let's say there is some parent nucleus that undergoes an alpha decay and gives you neptunium-93-237. Can you pause and predict what the parent nucleus be? Its atomic number and the mass number. Can you pause and try? All right, again, it's an alpha decay, so I know a helium nucleus must have been thrown out. Therefore, I can now predict, well, there is 93 in the daughter, 2 came out, so the parent had to have 93 plus 2, 95 protons in it. And similarly, 4 particles came out, 237 is in the daughter nucleus. That means the parent must have had 237 plus 4, 241 total number of particles in it. And therefore, my parent nucleus would be having an atomic number 95, which is over here. AM stands for americium. And so there you have it. That's my parent nucleus. And again, you can see, if you look at the periodic table, after the alpha decay, we've gone 2 elements to the left of the periodic table. So you see, all we have to do is keep track of total number of protons and neutrons. They stay the same because nothing is changing. The total number of protons and neutrons here will be the same as the total number of protons and neutrons here. And if you keep track of that, we'll be able to predict what our daughter nucleus would be or what our parent nucleus would be. Now, there is a reason why I took this example, because this is the radioisotope used in smoke detectors. But how does alpha decay help us detect smoke? Let's see. The heart of these radioactive smoke detectors will contain 2 plates connected to a battery so that they have a positive and a negative charge. And you have the americium source at the bottom. Now, the americium is going to give out a lot of alpha particles. But so far, did you notice something about the alpha particles? They have 2 protons in them, but they don't have any electrons because they came from the nucleus, which means alpha particles have a +2 charge on them. And since they're moving with a high speed, they can now knock off a lot of electrons from the atmospheric particles over here, from the oxygen, nitrogen, and all the other atoms. And that's why we'll now end up with a sea of electrons and positive ions. Now, of course, the helium nuclei will eventually pick up electrons and become neutral atoms, but eventually they leave behind a lot of positive and negative charges. As a result, this whole thing becomes a conductor now, and therefore there will be a current, a continuous current running in the circuit. Now, this process where the helium nucleus is able to knock off electrons is what we call ionization, and that's why we call helium to be highly ionizing radiation. But anyways, what happens when we have smoke? Well, it disrupts this process. It doesn't allow the helium to ionize a lot of these atoms anymore because of the smoke particles in between. That significantly reduces the current, and that is sensed by a sensor in the circuit, and the alarm goes off. This is how alpha decay can be used to detect smoke. I find this absolutely mind-boggling. But you might be concerned thinking that we have a radioactive element in our house now. Isn't that dangerous? Well, in general, radioactive elements are dangerous, but here's the thing about alpha particles. Sure, they are extremely ionizing. However, they don't go very far. They can be easily stopped, say, by just a piece of paper because they're so bulky. And therefore, although they have a high ionization power, they have very low penetration power. And that's why none of the alpha particles will even leave the casing of your smoke detector, and so you don't have to worry about anything. But what if you decide to now open up the smoke detector to have a closer look at the americium? Well, now that can be dangerous because you might have some neptunium-237 lying around somewhere over here, floating around. You might ingest it. Neptunium is also radioactive, and therefore now you have radioactive elements inside your body that can be dangerous. So don't do that.